Okay, so one of your classmates asked me to work some probability applications to the central limit theorem. So what I decided to do was grab a homework question from my stat lab. This is from homework number 15, question number 1. So let's give a look. It's talking about pregnancy times of an animal. All right, so it says that the lengths of pregnancies are approximately normal with a mean of 122 and a standard deviation of 12. All right, so let's look at letter A. It says, what's the probability that a randomly selected pregnancy, and that's for one person here, is less than 118? All right, so that kind of gives it away. The randomly selected pregnancy, that's a time, which is a random variable, it's x. And this is less than 118, kind of describes what that probability statement is going to look like. So let's go ahead and draw our bell curve. So here's the mean of 122. I like to put the standard deviation up top so it's out of my way. And let's go ahead and pop the 118 on there. So here's x, this is 118. And it's talking about the probability of x being less than 118. Now less than means shade to the left, obviously, so we'll shade left of that 118. Now theoretically this shade goes on and on and on to the left forever, to negative infinity. Now we're talking pregnancy time here, so either you've conceived or you haven't, so I'm just going to call this 0. I'm going to pick a common sense value down there. Now of course in the calculator there's no symbol for negative infinity, so if we want to, we would like to use the negative infinity, we would use instead negative E99. So whether you put negative E99 in your calculator or 0, you're going to get the same result. So we'll use the normal CDF operation. We've been using this operation for a while now. So normal CDF, and the syntax for normal CDF is lower bound of the shade followed by the upper bound of the shade. So the first two inputs describe the shaded region, and then the second two inputs describe the shape of the distribution, which is the center is 122 and the standard deviation is 12. All right, so let's go to our calculator and work this problem. So I'll go second bars, normal CDF, and I believe I typed this in already. So the lower is 0, the upper is 118, and the mean and standard deviation of 122 and 12. Let's give a look and make sure I didn't miss anything there. 0, 118, 122, 12. Yep, okay, that looks pretty good. So I'll paste that in. If you have the old version of the calculator, this is the this screen you see. You don't have that prior screen. This is the newer version. 0.3694 approximately. So 0.3694. Now if you look at the answer, it says 3707. And that difference is just due to rounding with z-scores and using the calculator, which is more accurate than say a table. The MyMathLab results are actually worked assuming that you're using a table. MyMathLab has allowances for those differences. All right, let's give a look at the next one, because the next one's a little bit different. So what would it be? What's the probability that, and here we go, a random sample of 26 pregnancies? All right, well, we're not talking about just one pregnancy anymore. It's talking about 26 pregnancies. Now, if you're going to have 26 people and each of them has their own pregnancy time, you're not going to talk about each individual person's pregnancy time. The idea here is that you find the average of the 26 pregnancy times and talk about the average. And look how the question's worded. Random sample of 26 pregnancies has a mean. Now, that's a mean for 26 people. So that's an X bar. So they're asking you for a probability involving X bar. And again, 118 or less. So that statement is a little bit different. So now, what clues you in that, this is central limit theorem is typically the fact that you're given an n. N is 26 here. But what really gives it away is that we're talking about a probability of a mean. So the probability, the mean, X bar, is less than 118 here. And it says less than or equals to, 118 or less, which means less than or equals to. But, if you put an equals to bar into there, it's the same thing. So it doesn't matter, because remember, theoretically, that's a continuous variable and the probability of hitting that number is 0. All right, so remember the mean of the sampling distribution, we call it mu x bar, is equal to the old mean, which is 122. But the standard deviation of x bar, well, that is not equal to the old standard deviation. It's actually equal to the old standard deviation, which is 12, divided by the square root of the sample size. I'm kind of running out of room there, as you can see. So that's 12 divided by radical 26. All right, so let's pop our probability region on there. So here's that 118. So remember this 118 now, let me get this out of my way, it's a little too close. This 118 is a mean. So when I shade left here, I'm not talking about the one person being less than 118. I'm talking about the average of the 26 people. So the probability x bar is less than 118. So again, what clues you in this essential limit theorem is that we're talking about a probability of an average. Mechanically, you're going to work this exactly the same way. It's going to hardly feel different. So normal CDF. Lower bound of shade 0, upper bound of shade 118. Again, the first two inputs describe the shaded region. The next two inputs describe the shape of the distribution. So the mean is 122, and the standard deviation this time is actually the standard error, which is 12 over the square root of 26. And again, we'll work this in the calculator. Nice thing about the calculator is, this probability statement, in the normal CDF statement, when you look at them, they look virtually identical. What they differ by is obviously the central limit theorem application. One person being less than 118 versus a group's average being less than 118. So the only thing I really need to change is, this thing here. The standard deviation, right? It used to be 12, and now it's 12 over radical 26. So when you have something like that, you bring up the last thing you typed by hitting second enter. It brings up the last thing you typed. I hit enter twice, sorry. Second enter, brings up the last thing you typed, and then you can just go ahead and divide by the square root of 26. So notice how the probability changes drastically. 0.0446 approximately. So 0.0446. Now the answer that my math lab gave is exactly that. So there was no errors there for the rounding. The z-scores must have been very close in terms of the two decimal approximations. All right, now the next question, if you read it, it's exactly the same question. But instead of talking about 26 pregnancies, they're talking about 57 pregnancies. And they're still talking about the same probability statement. So the reality, to work the next probability, all you really need to do is change this one thing. Change this n. So the n for question C changes from 26 to 57. But, virtually everything looks the same. So mechanically, it's going to feel the same. So if I go back here and hit second enter and change that 26 to a 57, here's my new probability, 0.0059. So for part C, when we have an n of 57, the probability that x bar is less than 118 is about 0.0059. Now that's not even 1%, right? That's about 0.6 of 1%. Showing you that it's very unlikely. And if you look at my math lab result for that was 0.0059. Now what's funny about this is if you think about question C, if they're telling us the mean is 122, then think about it. You reach into the distribution, you grab 57 people, and you find their average. Now, if the average, the actual average of the entire population is in fact 122, when you grab 57 people from the population and find the average pregnancy time, common sense tells you that average should be 122 or something very, very close to it. This question here that we just worked on, the probability of being less than 118 for a group of 57 people. Well, those 57 people, when you find their average, you're expecting that average to be really, really close to 122. So are the chances good that that average is less than something, far to the left? And as you can see, the probability is saying, no way is this happening. The probability of that is, not even 1%. As a matter of fact, it's 0.6 of 1% approximately. So the central limit theorem tells us that a group, it's very unlikely for them to deviate far from the mean at all. All right, I hope this helps. If you have any questions, shoot me an email. Thanks for watching.